All right, let's look at some situations where we are going to have a graph and we want to find some important values, all right? So here we have a graph of f of x, so just the graph itself, all right? What are the critical points? Remember, critical points are where it's undefined and where we have minimums and maximums. So that's at x equals 0 and b and E, all right? Those are our mins and our maxes, okay? And so those are the extrema there, all right? So same points, all right? We could have points where we had undefined. That would be a critical point and not an extrema, but not in this situation. Intervals of increasing, well, we're going up to the right from 0 to b, and from e to infinity. All right, that's this guy right here. Okay, increasing. Decreasing is on these sections right here. And so that's going to be at negative infinity to 0 and b to e. All right, so going downhill. Inflection points. So those are points where it changes from concave up like a cup, to concave down like a frown. And so right in here, it looks like it's changing, and I'm thinking that that's at A. And here it's down like a frown, but all of a sudden it's up like a cup. So right in here, oh, that's kind of a tricky one. I'm going to actually guess it's D, and it is D. So that's what we want. Okay, whoops. That is going to go right here. All right, concave up like a cup. Well, that goes from negative infinity to A. So because it's up right here. And then it's also up right here. D, we said, was our inflection point. That's what we decided. So from D to infinity, it's also up like a cup there, all right? Down like a frown. Well, that's from A to D. From here to there, that's concave down, all right? And that's it, all right? So that's just looking at the graph and understanding what those terms mean, right? All right? So now we have the first derivative, okay? So first derivative, we got to be careful here and think carefully about these. When we have critical points, well, that happens where the first derivative, f prime of x, is 0, all right? So looking at the graph, where is f prime of x equal to 0 or undefined? F prime of x is 0 at x equals 0, b and e. By the way, these two graphs have nothing to do with each other, so don't get confused there. Maybe it would be a good idea for us to use a g of x or something like that, but we didn't. Oh well. Extrema, all right? So extrema happen when we have a critical point, first of all, but also what needs to happen is the derivative needs to change. So we have this. What's helpful here is if we take this and we translate this into a number line for f prime of x. And we know that all the way up to the value of c, the derivative is positive because we're above the graph over here. And then we're below the graph, so the derivative is negative from c to f. And then we're above the graph over to the right, so that is positive. Okay? So now, looking at this here, we can see where does the derivative actually change? Well, we have it's going up, we're increasing. The function f of x will be increasing to c and then decreasing after c, all right? So c is going to be a max. Max at x equals c, and we have a minimum at x equals f. Point f, that is. All right? All right, so that's a key. So this 0 here is not an extrema in this case, all right? Because the derivative, the sign of the derivative does not change. Now, intervals of increasing and decreasing. Let's see here. We're increasing. Let's use our number line. So we're increasing from negative infinity to C, and then we're increasing from F to infinity. Where are we decreasing? That's when the derivative is negative, and so we're decreasing from C to F. Okay. Where's our inflection points? All right, so now we got to think second derivative. Second derivative comes from the slope, so let's make a number line here for the second derivative. The second derivative is the slope of the first derivative. All right, so we can say this, our slope up to the point 0 is negative. Then our slope is positive, going to B. And then the slope is negative, going down to E there. All right, going to E. And then from E to infinity, we're going up. Okay, the slope of the first derivative is the second derivative. So this little chart here, this little number line can be super helpful. All right, so with that now, let's just even ignore the graph, and we can see inflection points. That's where concavity changes. That's going to happen at 0. That's going to happen at B, and that's going to happen at E. All right? Where are we concave up? Well, we're concave up whenever the second derivative is positive. Okay? So that comes from 0 to B and E to infinity. Okay? And let's move this jazz. Concave down, looking at our, let's see here. The concave down is where we're negative, looking at our sine graph there. And so that's from negative infinity to 0 and from B to E. All right? So next, last but not least, let's sketch a graph using these derivative features, okay? So we know we have a max at C, somewhere at C we'll have a max. We have a minimum at F, all right? We don't know exactly where, but we just know it's a minimum. Now, this was not given a start value, so if we had a start value, then that'd be great. We might assume that f of 0 is 0, but that's not necessarily true, all right? But we need some kind of start value, so we'll make that up because it wasn't given to us. You just pick one if it's not given to you. We know we're increasing, so we're going to go increasing, and so let's see. So we're increasing, but we are concave down to 0. All right. So we're increasing, concave down. There we go. Okay. Increasing as we go to the right. Then what happens at 0 to B? Notice we're still increasing from 0 to B, but now we are concave up like a cup. All right. So we're concave up. Then from, we have it here at C. Okay, C, we know we have a maximum, all right? And we're now concave down, all right? So I guess I should move this maximum the way my graph is going. So we got an inflection point at B. So our concavity changes, all right? We're going up to our maximum. Okay, C is a maximum. Now we're at C. Let's continue on. Let's go to D. Anything happening at D? Nothing's happening at D. Next place that something happens is at E. So going from B to E, we have, we're concave down. Okay, like this is concave down. And we are decreasing from C going towards E. So we're decreasing concave down. And then from E to F, we know we're decreasing. And we are concave up because everything after E is concave up. So we'll need to be concave up like a cup. And then we're concave up and increasing because here we're increasing, F prime is positive, and we're concave up. Okay, there's a graph, something along that line. Again, this whole thing could move vertically or horizontally because we don't know the starting point, but that's a good place to start, to assume. All right, so there's a couple problems going from a graph to the information, all right, the special values. So here we got a function P of t that represents a population of fruit flies in the container at time t. And so we want to describe what's going on here, okay? And so here we have some descriptions. Well, these are all F's. Let's call this F, all right? So what's going on here, all right? We have first derivative is positive, and the second derivative is positive. So that means a little picture can be a big helpful. We're increasing, concave up. Here we have first derivative is less, so we're decreasing, and we're concave up, all right? So here we're decreasing, concave up. For this guy, we are increasing, concave down. So increasing, concave down. For this guy, we are decreasing, and we are concave down. So we're decreasing, concave down. There's our four possibilities. So what does this mean? So here, our population is increasing, okay? And we might say that it's at quicker rates, okay? So the population is increasing and the rate of increasing is getting larger. Well, here, population is decreasing, all right? So the population is decreasing, and the amount that it's decreasing is shrinking. So, okay, so we might say the population is decreasing by less each day. So less and less. How about that? Fancy way to say it, huh? As time increases. All right. Okay. So now we have what's happening here. We're increasing, but we're not increasing as fast. So the population is increasing, but the amount of its increase, or the rate, is getting less, okay? By a smaller rate, okay? As time goes on, all right? And so what's happening here? Here our population is decreasing because the function's going down. And the rate that we're decreasing is getting faster. Here, we're not decreasing very much. Now we're decreasing a little more, and now it's just dropping fast, okay? So we can say by more as time increases. All right? So let's keep it kind of the same. Okay? As time increases. So that's kind of the idea, all right? So it's increasing, decreasing, but the rate at which it increases or decreases is changing as well, all right? Okay, we're going to move on to a little mean value theorem here as we look at some more applications Okay, so here we want to know, does the mean value theorem apply on the interval given? And if so, what is the value that's guaranteed? All right, so two parts there. So the first part here is does the mean value, the hypothesis of the mean value theorem apply here? Two hypotheses: is it differentiable? And is it continuous? All right, so this is a rational function. So we know on this rational function, x cannot be -3. And is -3 on this interval? It sure is. So there's a break on this graph in that interval. So we can say MVT does not hold or not apply because it's not not continuous. It's got to be continuous and differentiable. So it's not continuous on the interval here. Whoops, come back. Okay. All right, that's the idea there. How about this one? Well, it's another irrational function. We know x cannot be 1. Is 1 on this interval? Nope, it's not. So that's not a concern, so we can go ahead and find the derivative, okay? So first thing here, let's find our secant line, delta y, delta x. And so that would be f of 4 minus f of 2 all over 4 minus 2. F of 4 gives us 1/3, and f of 2 gives us 1 over 1. And 4 minus 2 is obviously 2. So this is going to be 1/3 minus 1 all over 2. Let's multiply top and bottom by 3. How about? We can just a couple ways, but let's go like this, okay? So that would change it to 1 minus 3 as you distribute this little guy all over 6. And that's going to give us -2/6, which is -1/3. Okay, so that's our secant value, the slope of the secant line. And so now we've got to find the derivative of f. All right, and so we can think of this as x minus 1. You can use the quotient rule, or you can think of this as f of x equals x minus 1 to -1. I'm going to try that value that way. Using the chain rule here, derivative of the inside is just 1, and then times the derivative of the outside, the whole, which is -1, times x minus 2 to the -2. All right, so that's simply -1 over x minus 2 squared. All right, we want that to be equal to -1/3, okay? So -1 over x minus 2 squared equals -1/3. We can do a little cross multiplying, okay? And so we have -3 equals -x minus 2 squared. All right, I'm going to multiply both sides by -1. Let's just make this positive, in other words, okay? So 3 equals, and we have x squared. Oh, what are we doing? Don't multiply that out. So we want to get rid of the square there, so let's just square root both sides. Okay, and I made everything positive, so the square root doesn't matter there, okay? So we have the square root of 3 plus or minus, and x minus 2, add 2 to both sides. X equals 2 plus or minus the square root of 3. All right, so there's our answers. What is that? That's approximately 0.27 and 3.7. All right, 7.3. Actually, let's put a couple decimals of accuracy. Okay, and looking back, which one of those are on this interval? Well, from 2 to 4, only the second one is. All right, so our solution for part 2 is x equals 3.73. Okay. So, and we should have said part 1 here. Yes, MVT applies. All right, there's our solutions for B. Okay. Our solution for 1 says that it doesn't apply. So we don't need to do part 2. All right, cruising along here. C, we have 1/3. So this is a cube root here. All right, so a cube root's defined everywhere. So part 1, it is continuous and differentiable. So MVT applies. All right, it's everywhere differentiable. All right, so let's go ahead and find the derivative now. F prime of x is going to give us 1/3 x to the negative 2/3. Okay, also known as 1/3 x to the 2/3. Okay, let's find our secant line. So our secant line, delta y over delta x, that's going to be f of 1, right? Yep. F of 1 minus f of negative 1 all over 1 minus negative 1. Okay? And the cube root of 1 is 1. Cube root of negative 1 is negative 1. All right? And so 1 minus negative 1. Hey, those look a lot alike. So this whole thing is just equal to 1. All right? So let's set our derivative equal to 1. So we have 1 over, let's get a different color here, 1 over 3x to the 2/3 equals 1. Cross multiply, we're just saying that 3x to the 2/3 equals 1. Okay, and so multiply by 3. So x to the 2/3 equals 1/3, so x is 1/3 to the 3/2 power. And let's go to our calculator for that. And we get about 0.19. And that would be plus or minus. Okay, because we took a square root there. When you square root, it's going to be plus or minus. All right, so the answer here is x equals 0.19 or negative 0.19. Two solutions there. All right. And one more here of this type. So here, this is an absolute value function. And we got to know a little bit about absolute value functions. It helps to know that the graph of this guy looks like this. It's a V, and I didn't do that very well. It's going to touch the axis right here at -4. All right. And at that point, it's differentiable. So for part 1, it's not differentiable at x equals -4. Okay. So since -4 is in this interval, MVT doesn't apply. Okay. It fails the test. All right, that's how we use mean value theorem. Let's turn our attention to some L'Hopital's rule here. Remember with L'Hopital's rule that it has to be equal to 0 over 0 or infinity over infinity. So when we plug in 2 here, this goes to 0 as it is. Okay, so plug in 2, and we get e to the 2 minus 2, which is 1 minus 1, which is 0. And the bottom goes to 0, so this is going to 0 over 0. So we can take the derivative, limit as x goes to 2, derivative of the top is a little chain rule. Derivative of the inside is 1. Derivative of e to the x minus 2 is e to the x minus 2. And the constant goes away. Derivative of the bottom is 2x. Now we try to plug this in. Does that work? Yep, we can plug this in. We get 4 on the bottom. And we get e to the 0 on top, which is 1. So 1/4 is our limit. And down here, we plug it in. We plug in infinity. We see that this goes to infinity over infinity. So L'Hopital's rule does apply. So let's take the derivative of the top, and that's 2x plus 2. Derivative of the bottom is just e to the x. If you plug in infinity there, you'll see that it's still going to infinity over infinity. So we got to take the derivative again. We get 2 on top and e to the x on the bottom. And now we have enough to see that yes, indeed, when we plug in infinity, all right, or a gigantic number, this is getting huge. So we have 2 over a huge number, and that is 0. And that's how we use L'Hopital's rule, all right? Remember, it's got to be going to 0 over 0, or infinity over infinity, or some negative or positive infinity combination. Now we're given some information about a graph f of x, given information about its derivatives here, and a little information, yeah, that's all we got. We don't have information much about f other than f of 0 and f of 3 is 0. So it looks like we've got 1, 2, 3, so we'll mark that on our graph. Get those points here. We can start by marking our zeros. Zeros happen at f of 0 when x is 0 and when f is 3. All right. That's good to know. We also know it's continuous, so some nice smooth curve going on here. Okay, so let's see what's going on. When the derivative is 0, that's a possible max and min, okay, or if the derivative doesn't exist. If the derivative doesn't exist, that means we have a non-differential point, which usually means the graph is pointy, all right? So let's just start to sketch this out. We know that our derivative is positive for everything that's less than 1, all right? So less than 1, our derivative is positive. That means we're increasing. Okay, so we're going up. We're going up. At 1, looks like we have a maximum or a possible max or minimum, but what's happening? From 1 to 2, we're still going up. All right? And then from 2 to 3, we're going down. And then from 3 to infinity, we're going down. All right? So there's a general shape. Now let's talk concavity here. So what's going on? We got a negative, so we're concave down all the way up to 1. So we'll replace those with a curve. That's concave down. So we got concave down, and we're increasing. Now here the derivative is 0. And we notice that the second derivative is 0, okay? That means it's a possible inflection point, all right? And it is because now we're going up, increasing, and we're concave up. So this guy here is going to go concave up, and it's increasing to 2, all right? Now right here we start to see a problem with the problem, all right? Because if from here, we're at some point at 2, and we've got to now go down decreasing, and we've got to be concave up. No, I'm sorry, concave down. So we need to change directions, and it needs to go something like this. Okay? And so this, let me see. I'm going to change my height of these points real quick here. Okay, same thing. I'm just going to drop this down a little bit so we can see this a little better. All right, so we're scooping up, and now we're scooping down, but what happens is we got a sharp point here. So there's a problem. This is the problem. These guys need to be D and E, do not exist. So all these factors don't go well together. That problem is messed up. All right, just right there. But anyways, we got our curve there. It's not differentiable at 2. That can't happen going from the positive to negative like that. Now, here we are going decreasing but concave up. So that's our last bit there. So let's get rid of that. And we're going to go decreasing concave up. So right here, this is a non-differentiable point. So that's why at 2, the derivatives don't exist. And here, the derivatives are 0. It's an inflection point, and it's a critical point. But remember, critical point doesn't mean it's a max or a min. All right, it could be an inflection point, and that's the case there. All right. Here's a good little problem. All right, we want to make a table so that just make up some numbers so that f prime is greater than 0. And the second derivative is less than 0. So what does that mean? This means it's increasing. However, the rate at which it's increasing is shrinking. Okay? So if it helps, a little graph here, this means we're increasing. This means concave down. All right? So because the second derivative is less than 0, so we're increasing by a lot, and then not quite as much, and then not quite as much, and not quite as much. All right? So 1 is whatever, some value, okay? 2 is bigger than 1 because we're increasing. 3 has got to be bigger than 2, but not as big of a jump. I don't know, let's call it 7. And now 4 has got to be bigger, but not quite as big of a jump. Let's call that 8. So the first derivative tells us that we're increasing. Okay, that's true. But the second derivative says we're increasing by not quite as much. 5 is our big first jump, and then we only jump by 2, and then we only jump by 1. Now, you could pick any numbers you want, but the difference in between them has to be shrinking. That's because the second derivative is less than 0. All right, we're kind of decelerating here.